Okay, we're going to have a quick look at this year's Advanced Notice article for the second physics module, so for AS level. I've got another one for Unit 5, so the A2 level one, so if this doesn't apply to you, then just go out to my channel and check that one out. It's really good to get a good understanding of this paper because all the content's in the article, and if you know it well enough, then it gets a good basically third of the marks in for the whole paper, and that's very useful because it's a lot easier to get these marks than it is to get on something that you don't know will come up in the exam. This stuff you know will come up, so get some good revision in and you should be able to do it quite nicely. There are some online questions, so ones that another school have written, and there's mark schemes solutions to them, so I'll put them in the description as well, but it's just good to go check out and get some practice on the relevant material for this advanced notice article. But what we'll do now is have a look through the content in here, so all three of the sections: dot plots, systematic errors, and measuring the speed of sound, and we'll go and have a look through all of them and see what may come up and a couple of little solutions to possible questions that they might ask. So the first thing is about dot plots. So hopefully you know what a dot plot is. If not, it basically tells you. So in a simple experiment, the extension of a spring is measured with a ruler with standard laboratory mass of 1 kilogram attached. The experiment is repeated 10 more times and the results are presented as a simple dot plot as shown in figure 1. So in the dot plot you just have basically a pen or paper and mark where it is. So they stretch the spring and they mark down where the extension goes to, and then that's their dot plot done. And they've done this 11 times in total, and these are the results that they get. So first of all, we'll actually look at the force of a spring equation. So F equals kx. So what does that mean? That's saying that the force is proportional to the extension. That's a really bad X, but I hope you can see it. It also means that for simple, this corresponds to simple harmonic motion, so a simple harmonic oscillator, which means that when you stretch it, there will be, if you imagine a sort of spring system like that, with mass on the end. So you stretch it this way with an extension x, and then there's going to be a force acting in the opposite direction, trying to squish it back up. And likewise, if you squeeze it in too much, then the amount that you've squeezed it in will cause a force to go in the opposite direction. So that's all this spring really is. And they're just measuring the extension they get to do it with an applied force. You can also have a look at the energy stored in a spring, so that's something you'll be likely to ask. It could be, once you've calculated the mean of all the values, it could say what's the average energy stored in the spring when it's been extended. So then you just use E equals half kx squared, or E equals half f of x. So k is obviously the spring constant, and if we look at what it says at the end, that's the final calculated value of the spring constant k. So that will be the thing that you're looking to find. So it will be after finding the mean and after finding the spring constant, then you can find the energy stored in the spring. So that's something that's likely to come up, so make sure you know that equation. I think it comes in the formula booklet anyway, but it's just a good one to know. So we'll look at what it says about the data in the plot after as well. So it says you can look at the distribution and range of values and set data to find its mean and uncertainty. So if you've done statistics, maths at A level, then you'll think, oh, uncertainties, that might be something to do with standard deviation. In this case it isn't, so it says spread of the data, which half the range gives a useful estimate of uncertainty. So you shouldn't need to do anything like standard deviation in this question. It's just being able to find the range of the data and half it to get the spread. So spread equals range over 2. So it tells you that, but you just want to be able to use it, and obviously hopefully you know how to find the mean. So you add up all the values, so 2.1 plus 3 times 2.3 plus 3 times 2.4, etc. And then you divide it by all the ones left. So why haven't I included 1.8? Because I'm suspicious it's probably going to be an anomaly, so I'll calculate the mean and the spread of the data without the 1.8, and then I'll see, using this sort of rule it's got in this section here, so if a value is twice the spread above or below the mean, then we should exclude it from the calculation of mean and spread. So in this case I've done it without 1.8, and I get a value of 2.41 for the mean, and then a value of 0.3 for the spread. So then I look at twice the spread, that's 0.6, and then if we go from 2.41 to minus 0.6, that gets us 1.81. So the 1.8 is outside of the spread of the data in this case, so it can be completely ignored. Now you might be thinking, shouldn't I do this calculation with 1.8 in first and then see? I thought that a little bit as well, but it says here about possible outlier, any value that lies more than twice the spread above or below the mean. So if you did that including 1.8, so including a suspected anomaly, it would always be included because you're just adding or minusing the whole range from the mean. So if you did it with the with 1.8, then the spread of the data would be 0.45. So you'd have 0.45 as the spread instead, and 2.36 as the mean. But you don't want to do that because 2 times 0.45 is 0.9, which is the whole range of the data. So anything would be included if you included 1.8, because it would include every single point. You would take the range from the lowest point to the maximum point. You get 0.9, so anything in between that, add or minus 0.9, would be included. So you want to do it without the suspected anomaly first, and then see what happens. And like I say, if it's twice the spread above or below the mean, if it's outside twice the spread above or below the mean, then you can exclude it. So we calculate our mean and our spread of the data to be 2.41 and 0.3. So just double check that for yourselves and make sure you can calculate it correctly. If you get a different answer, then double check it, and it probably just means I've gone wrong somewhere. Now last bit, it says about the uncertainty on the extension x can be used to determine an uncertainty in the final calculated value of the spring constant k. So our uncertainty on x, if you take it as a percentage uncertainty, 0.3 over 2.41 times 100, and that gives us 12% uncertainty on x. And then we look at what's the equation for spring constant, so F equals Kx, so F over X equals K. So in this case, the if there's no uncertainty on F, then it's only the uncertainty on X that matters, and I'll get an uncertainty on K. And because it's not adding stuff together or squaring things, then you'll just have the percentage uncertainty on X is the same as the percentage uncertainty on K. So K should give an uncertainty of 12%. So say you got the value of K to be, I don't know, 3 times 10 to the minus 5, what is it, newtons per meter. If you want it to be that, then you just do 3 times 10 to the minus 5 times by 0.12, and that gets you your uncertainty on the spring constant. That's basically it for the first section. I haven't been able to think of much else that could come up. It could go into simple harmonic motion, so looking at what happens when the spring's released, but I think that's quite unlikely because it outlines what the experiment is that you're looking at, and it doesn't seem to need to go into that range. So I think the main things is being able to calculate the mean and the uncertainty, so the spread of the data, and then just being able to calculate things like energy and other simple stuff from the equations it's given you. Yeah, so we'll move on and have a little look at the next section now. So the next section's a bit about systematic errors. So they were mentioned on this page as well, but I didn't go through them because go through them in a little bit more detail on this next part. Yeah, they're mentioned. I know they weren't mentioned, but you just got to be aware that with a ruler you can have a systematic error as well. We'll talk about that more in this next little section. So, systematic errors. So these are different from random errors. So they're not random by nature, they're just systematic. And that means that they'll be the same on every single result you get. So it's not going to be some sort of random variation that you can reduce by taking more readings. It's just going to come up on every single one. So it gives an example. So tape measure becoming stretched over years, and an ammeter that reads 0.01 amps when there's no current. But the one we're sort of interested in for the previous one that we're going to look at an example is a ruler. So it goes from whatever we'll treat it as a 15 centimetre ruler. And usually if you notice on a ruler, so if you notice on a ruler I have 0 slightly off. So you have to kind of account for whatever that thing is there, and then we'll go up to 15 centimetres at this end. So if you don't account for this little bit here, then you'll always have a zero error of some sort by about like 0.2 centimetres or something small like that, but it'll still be there. The other thing is if it's become chipped over time, then you could end up with the end of a ruler that looks something like that, with this one being 1 centimetre instead. So you can have a 0 error of a little bit here and a big bit on this side. So there are loads of sorts of ways that you can get 0 errors on rulers by just looking at the end. There'll be a good chance it could ask you about one of them for the previous experiment. So it could say something like, or give you a diagram of a ruler that looks something like this, and the end bit chipped off, or a little bit extra on it, and say the student doing this experiment didn't look carefully at the end of the ruler, describe and explain the source of the 0 error, or something like that. So just be aware that they can come up, and make sure that you're able to identify a 0 error when you see it with a ruler like that. It says about the direction of the error. So if we have our endpoint like this, we've got a little bit extra there, so every value that we measure with this ruler will be larger than the value than the value that we've measured. So you'll be, say, measuring like 2.3 on the ruler here, but the actual value is 2.32 or something like that. So if in this case, then, so if extra beyond 0, then real value is larger. So then x, so the mean of x is larger than what you've measured, so the x should be larger, and then k should be less than what you've calculated. And the reason for that is because f equals kx, so then k equals f over x. So if we're getting some extra stuff on the end, then the value that we're measuring is too small, which means our real value would be larger, and because our real value is actually larger, then because it's k equals f over x, then if our real value gets larger for x, then our actual value for k gets smaller, because you're dividing it by you're dividing f by a larger value of x. And then if we look at it the other way round, so if we just change a few things, so we get rid of this end bit here, and like I said before, it's chipped at the end instead. We've got this as 1 centimetre, and we measure it to be 2.3 from the very end of the ruler here. We know 0 should be about here, so your actual value would be 2.28 centimetres. So then it all flips around the other way, so we'll see what happens. So if chipped end at 0, then real value is less. So if I write it in blue, then the mean of x is less. Then k should be larger. Change this to blue. And that means that x will be less. So you've got a small value on the bottom, so divide by a small value, and then you get a bigger value of k. So that's pretty much hopefully all there is to this area, so there shouldn't be much more than that. It should just be asking you about zero errors. It could give a completely different example, but I think it's nice to look at the previous one. It could be likely to ask you about the standard errors potentially that could come up in that section. Sorry, not the standard errors, the systematic errors that could come up in that section. And then there's a few more in the final section of this advanced notice article as well that we'll have a little look at. And it's good just to be aware of the potential systematic errors for other parts of the exam as well, because it's the data handling one, so it will be very likely that systematic errors are going to come up quite a few times in this paper, and you've always got to think about them when it asks this student's value isn't consistent with this student's value, what could potentially be wrong. You should be thinking random errors, so things like parallax error or a fluctuation in the data, and systematic errors, so things like zero errors where you've got something wrong at the end. So now it's talking about measuring the speed of sound, so you should immediately be thinking of waves, so v equals f lambda, and it's the speed of sound, so so it's good to look up what the speed of sound actually is, so that then when you go into the exam and you probably get some data and try and calculate it, it should roughly be in that region. So the speed of sound is roughly 330 meters per second. So it's just sort of outlining what the experiment actually is. It says you may wish to try this at school with the appropriate health and safety procedures, so it's probably a little bit late to try and do that now, but if you're still in school then maybe best to your teacher just to go through it. So there's systematic error in the experiment because the antinode is not at the end of the tube, a small distance beyond it. Then you do a little correction C, which then crops up in each of these equations. So it starts talking about resonances. So you're basically moving the tube up and down in the water, and you're measuring trying to find out each length of the tube when you've got a resonance effect. So resonance will be when you're changing the length, you're measuring like the amplitude, and you're going along, it's nice and normal, and then you suddenly get a massive peak. And this here is your resonance. And they measure the length for which each of these happen. So this will be L1. And they know from the theory that L1, so the first resonance, will be equal to a quarter of the wavelength. And they just know that from the systematic error you just do L1 plus C to get a quarter lambda. And they go on to this last bit, L2 minus L1 equals half the wavelength, so they can use the two resonances they found to find half the wavelength, and therefore just double it and find the whole wavelength. If we look at what the actual aim of the experiment is at the end, so a graph of L2 against L1, most reliable way, calculate the speed of sound, and and then it talks a little bit about uncertainties. So it's saying L2 minus L1 against 1 over the frequency. So what would that graph look like? Well, if we look at the equation we've got here, so L2 minus L1 equals half lambda. So lambda equals V over F. So in theory, L2 minus L1 equals 1 over 2 V over F. So if we say L2 minus L1 is Y, then we've got Y equals half V, and if we say 1 over F is X, so we've got half Vx. So you've just got a graph of Y equals mx, where m equals half v, so half the speed of sound. So your graph is literally just going to look like, and it doesn't even have a constant added on the end, so the graph should just look like that, where the gradient is v over 2, and your x-axis will be 1 over f in hertz to the minus 1. It's another thing, just make sure you know all the units of the values you're going to be using. So I had the spring constant earlier, so that's newtons per metre, and frequency is obviously measured in hertz. We've got things like meters and meters per second in there as well, but you should probably be able to work them ones out. But if there's any you're unsure of, just look up what the units of it actually is, just in case they come up in the exam. And then the y-axis will be L2 minus L1. So it's very likely to have a graph in this question or ask you to draw one. So make sure you know what it looks like. And what I'll probably do is have a graph like this with a load of data points plotted on it. And then say something like identify the anomaly, and then you just circle the anomaly. It could also have all the graph and loads of data points plotted on it and a table as well, and it will have some values missing, a couple of values missing from the table and a couple of values missing from the graph, and ask you to complete either or both of them. So just make sure you know what it's roughly going to look like. I think that's about everything. Oh yeah, so the resonance graph as well, it could ask you to draw that or identify the correct resonance plot. So it tells you a little bit about the resonance that we're expecting. So you should have 2 resonance peaks, and it tells you in the paper that the L2 resonance is quieter than the L1 resonance. So what you'd expect is something that's going to look a little bit like this. So you've got L1 here and L2 here. So it could ask you a little bit, it could ask you to identify the correct plot from a selection of 4 or something like that. It could ask you to label the graph with the resonances L1 and L2. It could ask you to calculate what L2 minus L1 is from a graph given to you or something like that. Just make sure you know roughly what that looks like. It says, I've exaggerated this a bit, it says L2 is more difficult to hear, so it's probably more likely going to look something very small like that. And it could even be really close to the large resonance, because that makes them even more difficult to hear. But just know that there's going to be 2 resonance points along there, with the second one being a lot smaller than the first one and not being as clear to here. And you calculate the difference between the two resonance points. That equals half of the wavelength. Use V equals frequency times wavelength to find that L2 minus L1 equals 1 over 2 V over F. And that's just going to be a graph of L2 minus L1 against 1 over F with a gradient of V over 2. Okay, so keep having a little look through that. Have a go at the questions. They're from Matthew Arnold School, and I'm going to put them on the description of the YouTube link as well. So have a look at them, go through them. They are usually a lot more difficult than the ones that are actually going to be in the paper. I remember that from a few years back when I did it. The ones from Matthew Arnold School I found more difficult than the ones in the actual exam, but they're good. They're still good practice, and it gets you thinking about extra stuff that they can actually ask in the paper that I might not have come up with, or you might not have thought would be asked. So good luck for the exam, and just make sure that you keep revising this section, because it can get quite a lot of easy marks. If you found this helpful, then like the video and subscribe to my channel, because I'll be doing more for your exams next year as well. So yeah, I'll go through a couple of papers over the summer, and you can come up and watch them whenever you want. Okay, yeah, good luck and revise well.